Hello, so in the last video I kind of gave you an introduction to what a power series actually was and kind of where it came from. But this is actually, one of the uses that we can make in ODEs of power series. We can actually use power series to describe something useful. And the use is for analytic functions. So in other words, we can derive some definition for this thing called an analytic function. Now, an analytic function, this is for real numbers, although complex or real functions, although complex functions is slightly different. It's along the same kind of lines. Okay, so an analytic function is basically a function that can be written as a power series around some point. Okay, so in other words, if we have a function, let's say cos x, this is analytic. This is analytic. Because we can write the power series for that. We can evaluate the power series of that by doing the Taylor series, okay, around x naught. So the power series of Taylor series around x naught. So here's the Taylor series. So here's the Taylor series. So in other words, we evaluate the Taylor series of this function here, cos x, around the point x naught. Okay, and because we can evaluate it around x naught, then basically we say that cos x is an analytic function. Okay, because it has a power series around x naught, so therefore it's analytic. So an analytic function is a function that can be written as a power series around x naught. Okay, another way of saying that is the function is analytic at x naught. Okay, so that's another way of saying it. So we basically say that cos x is analytic at say 0 or 3. In actual fact, cos x is analytic at every single value for x. Okay, it doesn't matter what value we put in there. We can always find a Taylor series expansion for that function at every single point. So therefore, cos x is analytic at every point of x naught. Okay, so basically an analytic function, in ODEs at least, is a function that can be written a power series around x naught. Another way of thinking about it, because a Taylor series, as you can see, a Taylor series involves the derivative. Okay, the only reason, or perhaps one of the only reasons, why we wouldn't have why an analytic function wouldn't be analytic at a particular point. Say, for example, let me just show you by an example first, and I'll come back onto this. Say, for example, 1 over x. Well, 1 over x has a derivative at every single point. So it has, it's a function. It can be written as a power series at every single point except at x equals 0. Okay, so in other words, at x equals 0, so x naught equals 0, say, okay, what happens when this is equal to 0? Well, it goes to 1 over 0, which of course is infinity. So in other words, at the point x equals 0, we have what's known as a singularity. Okay, because it's a function, because at that point the function goes off to 0. So in other words, the function is not defined at that point, but it's defined at every other point. Okay, so basically the idea is that another way of thinking about an analytic function is that it's differentiable everywhere that it's continuous. Because if you look here, it's not continuous at 0. Okay, at x equals 0. So 1 over x is not continuous at x equals 0. Why? Because it goes off to infinity at that point. Okay, but it's differentiable everywhere else, everywhere it's continuous. Okay, because at all other points we can evaluate the derivative, and the derivative is given by this Taylor function or this Taylor series. Okay, so yeah, we can basically, because we can evaluate the function using the Taylor series, and the Taylor series depends heavily on the derivative. Okay, another way of thinking about what an analytic function is, it's differentiable everywhere that's continuous. Okay, but I mean, if you just want to learn that definition or just remember that definition, then that is absolutely fine. That's absolutely sufficient. Okay, so it's basically just an analytic function is a function that can be written as a power series around x naught. So for example, if you wanted to talk about this 1 over x, okay, it can be written as a power series around every single point. So therefore, it's analytic at every single point except at x equals 0. Okay, so in other words, it's not analytic at 0. Yeah, but it is analytic at every other point. So hopefully that kind of makes a bit of sense. Okay, another example of a function that sort of behaves like this is tan x. Okay, tan x, because if you put in odd multiples of pi over 2, if you put in odd multiples of pi over 2, so in other words, pi over 2, 3 pi over 2, 5 pi over 2, etc., and all the negative ones as well, you end up with an asymptote. Because if you remember the graph of tan, it goes like this. Okay, let me just try and draw in a point of reference. There we go. So this is the point of 0. This is pi by 2. This is negative pi by 2, and it repeats. So you have the same thing again, and the same thing again, and the same thing over here as well. So basically, where this asymptote occurs, the function is not defined. In other words, discontinuity. It's discontinuous at that point. Okay, at those points there, there's an asymptote there. It's not defined at those points. Therefore, it's not analytic at those points. But it's defined everywhere else. You can write a power series of tan x around all other points except at where there's an asymptote. Okay. If you want to think about the graph of 1 over x, graph of 1 over x looks like this. There's an asymptote here, and there's an asymptote here. So in other words, it's defined at every single point. It's defined at every single point either side of 0, but it's not defined at 0 because that's where an asymptote lies. Okay, so again, another way of thinking about it. Okay, so once we've got analytic in our head, then we can start talking about combining two functions and coming up with some useful properties of analytic functions. So for example, if f and g are both analytic at x0, so they're both analytic at the same point, then we can say that f plus g, is also analytic at x0. Okay, and again, f minus g is also analytic at x0. Okay, f times g is analytic at x0, and f divided by g is also analytic at x0. And if you're interested in that, go and have a look in the book, and there's sort of quite a nice argument presenting that. But this kind of makes sense that if these functions are both analytic at the same point, then no matter what operation we perform on these two functions, they're still going to be analytic at that point x0. Okay. So I know that obviously analytic functions often presents a lot of confusion because you ask people and nobody really gives you a straight answer. And the truth is because it depends what you're talking about. Okay, it depends what you're talking about. There's lots of different definitions for analytic functions, or there's lots of different ways of thinking about the same thing. So it depends which situation you're thinking about in order to get the definition which suits that particular situation. But for ODEs, the purpose of ODEs, an analytic function is just a function which can be written as a power series. So in other words, it has a Taylor series expansion around some point, and that point which we just call x0. Okay.